Just by way of review, if you've watched the previous part, we were talking about Euler's method. Okay, and so we said that if you have ODEs of the form of dy over dt equals some sort of function of t and y, you can implement this method that takes some sort of current value and then adds some function that provides a slope, okay, and then multiply that by delta t to move forward in time, and as a result you're going to get the next y value. And we talked about how the value at that next time is based only on the slope of the previous time only. But we can improve this estimate if we take advantage of, maybe the future slope. And so if we have an average slope of that beginning and the end of the time step, maybe we can kind of do a little bit better in terms of like what this value really is. Okay, and so essentially it's using kind of like a predictor of that future slope and then kind of a corrector method. All right, and we call this method Hoynes method. Okay, and it uses this predictor step. The good thing about the Hoynes method is that you don't have to do much more other than kind of Euler's method twice for every round. So let's kind of walk through what this means. So the predicted slope is the slope at the beginning of the time step. Okay, so this is nothing more than kind of saying, okay, well, the derivative at that time is going to be just a function of the time at ti and yi. Okay, and so we're going to use this as kind of like this slope value. All right, and so just like this Euler step, we can do the predicted value of this process as well. In this case, then, we're going to take the current time, we're going to do the function value, and we're going to just say, you know what, I'm going to use that predicted future y value inside another slope calculation. Okay, that's all it is. So effectively, you have the slope originally, okay, up here, and you have the slope for the future time right here, and then you're going to average these two slopes together. And hopefully that's going to give us a little bit better of a prediction as to what the best slope should be that we march forward in time with. So let's talk a little bit more about this right here. All right, so right here you can see that it's nothing more than the Euler calculation of the slope at that time equals I. And then we also have a function call, which is nothing more than the slope at that future time, I plus 1, which may use the y value at that future time, and then of course you just average those together. So effectively, then, you're going to have some sort of initial point right here. We can call this y0. Okay, we know it's happening at time t equals 0, right? And we can extract out the slope, okay, at that time is equal to 0 right here. All right, if we march forward in time, okay, and we found this point right here, we're going to call this yp. It's our predicted value of that first slope. We can plug that into another function call and extract out, well, the slope of that point right there. Okay, so I'm going to dial that down. That's going to be at, say, time equals 1. All right, so then what we do is that we take this slope, okay, that's that arrow, and this slope right here, we kind of average them together, and it's going to be something in between, maybe about that, okay, because this one is a little bit more horizontal than this one, and so the average is going to be this guy right here. Then finally we march forward in time, and this then is going to be our true y1. Okay? So effectively we have two slopes that we average together to then find out what the true direction is going to be, and so we call it kind of like the prediction and then the correction slope towards that next y1. All right, well, here's Hoynes' method, another example right here. You can see then that we're going to calculate, okay, y prime, or the slope right there. Okay, we're going to use marching forward in time to figure out the slope. Okay, that's the other y prime at that future time, at time ti plus 1. Okay, and then we're just going to average those two times together. We're going to average those two slopes together to figure out what this slope is. And then finally, okay, we're going to march forward in time, and that's going to be then our y I plus 1. Okay, our y at I time I plus 1. So it's nothing more than taking kind of that Euler and kind of correcting it with another slope so that overall we get like a really good average slope that then we can implement in, well, an Euler step right here. In C++, we're not going to show the example C++, but I'll show you this code. You can kind of play around with it. You can see then that we've got nothing more than kind of this function that returns the derivative information. Okay, right here you can see that it's that example 1 where we're returning nothing more than -1. Okay, we've got all these initialized values right here, which would be pretty self-explanatory. The most important part is talking about kind of this while loop right here. And it looks like I'm missing one space, so I'll kind of talk about that error, and maybe I'll recompile this before I post it on Learning Suite. That being said, we're going to step through, okay, until time is less than equal to t final. Okay, so it's somewhat similar to a for loop. You can do it this way as well. Okay, and we get the first slope right here, which then is going to be a function of the current time, okay, and the current y. All right, that's that first slope. Then we have this little prediction step right here. There should be a space right here. This should be a new line. Okay, so we have y plus the slope of that line to get, well, this predicted value yp. And then we use that yp right here in the calculation of slope number 2 at the end of the time step. Same function call, the derivative with respect to t plus dt, okay, that future time and yp. And then right here, okay, we do nothing more than do the average of those two slopes. And then finally we do, well, one more Euler step. We increment the time and we're good to go multiple times, and this would work out with our C++ code. With Hoynes' method now, we're going to do the same sort of thing. Okay, so we've got this function. It's exactly the same that we did when we talked about Euler's method. Here's the exact solution, so I'm going to use a lot of my code from beforehand. But the one difference then is that we're going to modify our code so that it's using the Hoynes' method right here. So in the meantime now, I'm going to shrink down, okay, the slides just a little bit. Okay, and I'm going to spend some time. I'm going to save this file, not as Euler's method, but I'm going to say it as Euler's and Hoynes method. Okay, to make it a little bit different, because what we're going to do then is going to take this little block right here, and we're going to modify it, okay, into Hoynes method. All right, well, the first thing we're going to do is that we might have different time values. So we're going to change dt into dth. Okay, if you have dth, then that's going to make this be dth. And then the time might be different, so we'll call this also time vector, but for Hoynes method right here. Well, if that's now th, this has to become th, and this now is going to be y for Hoynes method. Okay, and so Hoynes method will change these to YH, this to YH, 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 and TH. And of course, don't forget your DT, but change it to Hoynes size, just in case it's different than the Euler's method up here on line 26. Clear that command window for you. All right, well, if you recall then, the first step is kind of doing the predictor step, okay, which is nothing more than taking a normal Euler step. Okay, so I'm going to change this one not to YH, but I'm going to change it to YP. Okay, this is like this future value that's kind of temporary. We call it the YP or YP predicted. Okay, so wherever we're at, we're going to move and find out what the slope is, move forward in time, use that YP, and then we're going to take an Euler step where we do an average of two values, this one and something else. So I'm going to make some brackets right here. I'm going to multiply it by 0.5, okay, which is going to be the average of these two values. And now we need to go off and try to explore and change what these two values are. The first one is the same, okay. So over here you can see like that's right there. It's the same value with respect to ti and yi. But this one right here has a different y. It's got actually the yp. So we'll come in here and change this to yp for that predicted value of y. And then this one right here also is different. It's not thi, it's going to be thi plus 1. Okay, it's the next time step inside that time vector right here. Same sort of thing if you did this, you could do ti plus dth. Okay, this is going to give you the exact same result. It's going to take the current time and add a small little time segment to it. Okay, I'll go back to the original one right here because I've already established my time vector th up here. All right, well, that was Hoynes' method. All I'm doing then is going to try to make a better approximation or a better guess for what this is. Okay, and so then once I have YH, well, then I can go off and I can plot it. Okay, so I'm going to add then also another line. Okay, but now in this case it's going to be the time vector associated with Hoynes' method, Y Hoynes' method, and I'm going to make it have triangles and make it green. All right, if I add one more line to this, okay, I need to change my legend. Okay, so what I'm going to do for the time being is I'm first going to suppress that Euler's method step. Okay, then I'm going to copy this legend. Okay, and instead of Euler's method, I'm going to make it into Hoyne's method, and I need to change dt into dth. Okay, I need to Control R that and suppress it, and now I need to make sure that I've got my right function. Well, for my anonymous function beforehand, this was from example 3, so I need to suppress that. I need to open this one up, Control T. Okay, T exact, I need to do the same sort of thing. Okay, and then I'm doing Euler's method right here. It doesn't really matter because I'm not plotting anything. I'm just going to compare Hoyne's method with the exact solution that we calculated from above. All right, let's hit run and let's see how I do. Oh, I have a little problem. I have an error in my color or line type argument. All right, let's go back and kind of see what's going on here. I've got T and G. Let's do help plot. Make sure I didn't make a mistake. So I wanted green, that's totally fine. But I wanted a triangle. Oh, it wasn't T. A triangle is actually this little symbol right here. All right, well, here is the result, okay, for example number 1, and you can see that I've got my axis set to be from 0 to 8, so I'm going to go off and change that. And then I might move this from southeast to northeast. From here, change this to northeast again. And I want to go from 0 to 4, but then I want to stop at, let's say, I don't know, 1.5. That might work out. Okay, so what we can see then is that Hoyne's method is doing a pretty good job, even with a large dt value of 0.5, of trying to position itself along the exact solution. And if we zoom in, okay, we can see that, yeah, sure enough, there is still some error in between those two lines, but it's doing a lot better than the other method. So let's actually turn that one back on, Euler's method, okay, by doing a Control T. Okay, in this particular case now I need to add another legend which has all of these points. So I'm going to take this line out, and I'm going to pop it in right here. Okay. So we can see then is that the legend is going to have 3 entries. The first is going to be the exact solution. The second one is going to be Euler's method with dt. And the third one is going to be Hoyne's method with dth right there. All right, let's turn that back on, hit run. Okay, and now you can see with the same dt of 0.5 for Hoyne's method and 0.5 for Euler's method that Hoyne's method is doing a lot better of a job. Okay, and in fact, at the same size, it's doing really quite well. In this particular case, Euler's method is underestimating and Hoyne's method is overestimating. But if we decrease dt on both of these, let's see how we do. So I'll change Hoyne's method to 0.25. Euler's method is 0.25. Run it again. Okay, and now it looks like the green line, or Hoyne's method, is almost directly on top of the exact solution. We can kind of zoom in here and let's see how we're doing. Okay, and sure enough, we're doing phenomenally well with the Hoyne's method at the same dt value, because now we're doing a little bit better in terms of predicting that future slope a little bit better because we're having 2 values instead of just 1. The analogy or comparison is similar to the trapezoidal method that uses 2 points for one line segment, or Simpson's 1/3 method that uses a little bit more information, does a quadratic approximation of the function, and then can do a little bit better at approximating the area under the curve. All right, well, let's change these values to 0.1. Looks like they're both doing really quite well, but if we zoom in here a little bit more, okay, we can see that sure enough, Hoyne's method is doing almost perfect. Just a little difference between these 2 lines, but Euler's method is still off by maybe a significant amount based upon the accuracy that we require for our application. Okay, well, coming back here, let's take a look at what I've got for the slides. Well, we can see then that I've got Hoynes method compared with 0.5. We've got Hoynes method at 0.25 and Hoynes method at 0.1 like we did before in the MATLAB. Let's talk about the next example. Well, the next example is almost all ready to go. Okay, so I'll reset these to 0.5 and 0.5, and then I'll just change my function to be example number 2, change the exact solution to be example number 2, and then I'll be ready to run and see how it compares. Alright, well, this is what I got, and sure enough, there's a problem with the axes, so I need to go off and change that. So let me just do that here real quick. Let's go to 0.8, I believe. Okay, and then of course I also move the legend down to the southeast. So let me come in here and just do a copy paste. And now we're good to kind of talk about this. So again, Euler's method is following kind of the overall trend, but it's off by quite a bit the whole time. Whereas Hoynes' method is doing a phenomenal job and in fact even crosses the exact solution a couple of times at the beginning and at the end. So what we need to recognize though is that because Hoynes' method is doing an average slope, okay, for this line, it's doing a much better job at predicting what the point is going to be at 0.5. Another way of looking at this is that this slope right here, this green line, the very first average slope, is going to be the average of these 2 points right here. This one right here and this one right here. And you can kind of see that sure enough, if I average the two slopes right here and here, I'm going to have this slope right here. All right, well, that's day t at 0.5. Let's shrink this down to 0.25 like we have been before. Okay, we can compare these two methods, and again, Hoynes' method is doing much better. Let's go down to 0.1 for both of these. I bring it back into focus, and sure enough, the green line is almost directly on top of the black line. Let's zoom in to just a little portion of it right here. Okay, we can still see that there's some error between Hoynes' method and the exact solution, but there's much greater error between Euler's method and Hoynes' method. The other comparison that we can do is that if Hoynes' method is at 0.5 and Euler's method is left at 0.1, we have approximately the same amount of error, in the sense that if I zoom in right here to a little section of our program, or rather application, we can see then that there is definitely some error, okay, with Hoynes' method between the green line and the black line, but that's at a dt of 0.5. Whereas the same error approximately, okay, with Euler's method at a dt of 0.1. So I had to do a whole bunch more work, and in fact I had to do a whole bunch of more function calls, 5 times more function calls in fact, for the same amount of error, which means Hoynes' method is much better in terms of efficiency and in terms of accuracy. Alright, well, going back to the slides then, that'll be posted on Learning Suite. We've got, of course, the comparison that we saw beforehand of 0.5 between Hoynes' method and Euler's method. Then we kind of step through different values of dt of 0.5, 0.25, and 0.1. All right, let's finish up with example number 3. Now that you've kind of seen this process, we'll move really quickly. So 0.5 and 0.5 for Hoynes' method and Euler's method. Whoops, there's a little typo right there the whole time. Sorry about that. I will comment these ones out. I will uncomment these ones out so we have the exact solution set. We'll do 0.5 and 0.5 again. Okay, I think the axis is the same. Let's hit run, we'll see how we do. All right, well, we finally have kind of an interesting output. If you recall, we looked at Euler's method with dt 0.5, and we talked about how it was unstable and slowly this value was increasing. But Hoynes' method is also kind of struggling, which means then that we're starting to reach the limits in terms of what Hoynes' method could do to kind of fix the problem that Euler's method had. So let's first of all decrease dt for both of these. Let's see what happens. We'll do 0.25 for Hoynes and 0.25 for Euler's method. Okay, we've still got some problems. So both these methods look like they're insufficient in trying to track that exact solution. Let's go down to point 2. All right, so it looks like Euler's method, as before, is at least bounded now. Okay, the error is kind of the same for the whole process, and Hoyne's method is kind of doing well, although it's not tracking exactly well the exact solution. So let's keep on decreasing this down to 0.15 for each one of these methods. Bring the figure back in. All right, and so now we've got Hoyne's method, which is doing a pretty good job. Okay, especially doing that linear part, but we know that Euler's method is going to do pretty good at that linear part as well. And now it's kind of a discussion about this part right here, where based upon focusing in on this, we can see that maybe Hoyne's is doing a little bit better, although it's underestimating the exact solution, and Euler's method is crossing the exact solution. So we'll finish up with 0.1 and 0.1. I bring it into focus. I'm going to zoom in on the first portion, which looks like a little bit different. And now finally Hoyne's method is starting to really be beneficial because it's a small enough dt such that it's really minimizing the error between the exact solution and the Hoyne's method approximation of it. Let's take a look at the slides then that's posted. You saw this one before, 0.2 for dt, 0.15, and then 0.1 for Hoyne's method. Oh, and I've also done 0.05.